Okay, now moving to the analog network coding. So there are two different things, analog network coding and physical layer network coding. The idea is now to move it away from the packet idea, really on the symbol level. So what does it mean? As we said, we were in the packet domain. When we look into where network coding can be applied, you will see this later. It can be applied on the higher layers, on the lower layers. And when you do it in a physical, on the physical layer, there's analog and physical network coding, right? And this is the lowest layer. And now we are coding symbols. We are not coding packets or bits. We are coding more symbols. And this time it's not the symbol that we used or that we will use later in Kodo. Here is really a physical symbol. And what we will try to do is we don't want to receive packets from one side or the other and then see how we digitally do it. We just do it on the air. So there's something that coding symbols, superposition of signals, right? And here what we do is, while in the digital domain, we always try to separate two packets or two senders from each other to avoid collisions. Here we are forcing sender and receiver to bring us collisions where the collision is actually the coding. So how does that work? Here again, Alice and Bob, right? Very easy. The blue and the yellow one would like to send something to each other, and the blue one sends it to the relay forwards it to the yellow sends something to the relay, and the relay will forward it. 4 time slots. Exactly what you have done before, right? Pure relaying. Now, if you do digital interflow network coding, you could say we are both sending to the relay, and then in the digital domain, we are coding this. We are performing an XOR bitwise on the incoming packets at the relay and broadcast the outcome. And then you see we only have the 3 time slots. Even that was explained beforehand. Now the analog, the physical thing that could happen is we are sending at the same time. No, not at different times, now at the same time. And the relay will get a superposition of the signals, and whatever he gets, he will broadcast it. So this only has 2 time slots. But how can this work? How can this really become a meaningful information when we do that? So it seems more difficult, and it is. If you really would like to implement it, then you know that we have done a lot of in the digital domain, in the analog, we're doing something. There will be maybe one exercise where you can go and look into that. And what we will do here is that we make it very easy to reduce the number of necessary transmissions. And we look into things like throughput, energy, and security. So throughput and energy, I think that we have done before, but what is with security? This is a new KPI, right? So the physical layer network coding that was presented by Zhang and others in 2006 was a very simple example. No fading, and we look at a bypass signal. Here you receive a received signal where we have a signal over T1, signal 2 over T, sending at the same time to the relay, and the relay will then take the incoming signal, the combined signal, the superposition, and just broadcast it. And what is this, right? So the received signal that he will have is, okay, I see S1, S2. There will be also noise, right? And if you have a very simple one, BPSK signal whatsoever, you can put this together in the 2 different amplitudes plus the noise, put it together, and you see, okay, there's a cosinus and a sinus, WT, and then you have A1, A2 as 2 amplitudes that you put together, and the same for B1 and B2. But this is what we receive. What will we send? Okay? So we could amplify and forward, so which means whatever we get, we also sending out. But we can do a transformation and say we can also decode and forward, right? If we do decode and forward and say BPSK, I hope that you know what BPSK is. You have a high or low signal symbol, and this you just map. There's also QPSK and others. BPSK is the most simple one, right? Now, if you look at the received signal and you see that you just want to understand A1, A2, there is no sinus part in that. All the B's are 0, and the other one could be minus and plus 1. And then you only look into the additive amplitudes. And now you have 3 different possible outcomes of A1 plus A2. -2 and 2, That's correspondent if A1 and A2 has sent the same. And a 0 means they have sent different things. And the probability of this is 50-50, right, that it happens. So if we generate now S3, it's the one that we would like to broadcast, it's like an XOR operation where we say if the amplitudes are the same, whether high or low, then we say it's 1, a logical 0. And if it's A1 and A2 is different, then we say A3 is a -1. It's just indicating it. So what we try to do is the incoming signal has 3 symbols, right? And a BPSK has only 2. Now we are mapping. And for us, it doesn't matter whether it's the highest, the +2 or -2, because we map it to 1. And the 0, we map to the -1, right? So how does it look like? So what if we amplify forward, for example, right? Alice may send 2 symbols. This is BPSK and this is BPSK, right? So when we do this in the air, if we are sending, for example, this 2 things, like on the top, you get these green bubbles. And I said there's noise, right? Therefore, you see a little bit of different incoming signals here. If they send both the low, you get this one here. If they send different ones, you're ending up in the middle here. And I should make more points in the middle here because this will happen twice as much as the others. So the first thing is, as you see here, if we are both high end, right, then and this is the receiving signal. This is R3. And this is if both are low, right, -1, -1 gives a -2. Now they are different, +1, -1 gives a 0, or the other way around. Also 2 different signals, also a 0. Good. What we have to do now is the matching. I said already we need to give the higher and the highs +2 and -2 to the +1 and the 0 to a -1. Then we have 50-50 occasion that this happens. And when we send this out, you get again a little bit of noise here. When you send this, you will receive this here, and if you send this, you will receive this on that side. So the same for the lower part. Now, once you receive this, what does it mean, right? So if I'm Alice here, if I transmitted that one, and I receive a -1, what does it mean? Where is my calculated one? So we said, if we send the same, it's up here. If it's down here, we have the different one. So I'm sending this one, and I'm receiving this one. So this means we are different. That means this one is the one that we want to receive. You understand that? It's like the XOR. So once again, you get them. So what you receive from the relay is the green one. It tells you it was different what you sent. And you know that you have sent this, so it's this one. So if you say, I received this one, I have transmitted that, now you know it's here. So it's not really a secret because you see already by the yellow that also should then maybe be animated that you understand where it is. And other things are, you did, for example, you transmitted this, you received this, so this is calculated. And the other one is you transmitted this, you received that, this is one is the calculated. Okay. So the assumption was there's no fading, there's amplitude and plus phase distortion. But the fading makes it more difficult, right? So if you really want to implement it, it's not like this. Some of the stuff in network coding that we are discussing, you can take from the whiteboard, bring it to reality, and it works like a charm. Storage is such an example, right? You will see this later. But this one is really problematic because you also need perfect sync, perfect detection of a collision, perfect knowledge of packet use for decoding at Alice and Bob, the right packet to interfere, MAC, network impact. So how to make it practical? There's some work of Kati and others in 2007. It's called analog network coding. There's another one called zigzag decoding. This one you have heard already, right? And the zigzag, for example, is if you don't put your packets and they're not right above each other. So then you have to shift them a little bit. We have done this in the digital domain. I think it's easier for you to understand how the zigzag decoding works on the digital. You can work with ones and minuses, with ones and zeros. Here you have to calculate it with 1 and -1, which is more problematic. So this was the key intuition where we had in 2007 from Cartier and others. You see a signal from Alice and a signal from Bob, and you say, okay, this is already a part of Alice, this is a part of Bob, right? And this is where no overlap is. So this is the pure signal. And here we are overlapping. And now we are not matching the right symbols with each other. We have to recalculate the symbols. The method is the same, but what you will do now is to understand a header and a footer, which is more or less here. And then you see then with that you can do the zigzag coding. With that over here, and no, this one in the last part, you can clean it up in a zigzag approach as we have done in the digital domain, right? And then if you look into the gains that you get, gain over cope and gain over routing, and this is quite high. So this is the standard one, but this is the one, even a gain over the digital approach of network coding or digital interflow network coding. Okay, then if you talk about the zigzag coding, there is something which we can maybe have a look at to understand how this works more practically. Here you have two packets and they have two different offsets, right? They're coded in two different ways. And when you have the first chunk, this one, this is clean, right? From A, when this A is clean, you can just read it, put it there, subtract it from here, you get the 2, you bring it back, you see that this is clean now, you clean up the 3, bring it back, and this is the zigzag coding, what you're doing here. But you need two different offsets, right? This is just to let you know how it could work in the future. And if you understand that this collisions is not a bad thing, you can even use this for different transceivers. So you could send from different senders at the same time, many times. So if you have, let's say, n transceivers, you must send at least n times, and then you could clean up the symbols over there. That is quite interesting. Here's some work that you can have a look at. I will not go into detail too much about this. I would like to talk about the coded version, and as I said, there will be also one of our exercises where one of our colleagues can show you our analog network coding testbed. Here you see software-defined radios that can communicate. This is Alice, this is Bob, here's the relay. And then you can really see how these signals really match. It looks a little bit magic, right? But it's highly set up. So we need to synchronize them first, and we need to understand the phases. It's not so easy. It's not robust yet. But we put a little bit of emphasis into that. From our perspective, analog network coding was not so intriguing as, for example, the digital one, because you can just deploy it on any off-the-shelf stuff. Good.